Hey everybody on Zoom. We'll get started in just a second here. Yeah, right now. So the plan is just to go over the practice midterm that I wrote. Let me lower the screen maybe. Um, and then on Monday we'll start talking about the chapter 12 stuff, which is like the principles of counting and some combinatorics. I mean, it's really just like probability and a little bit of stats kind of stuff, but it's kind of, we'll do what we can. All right, so obviously, if you have questions along the way, please do stop me. I'll say two things. So after this, I'll post this video. I'll also post the solutions that are right here. I've already also posted the solutions I wrote before this. And the solutions I wrote before this might be a little bit more detailed than I right here. Worth taking a look at, I think. Let's go ahead and get started. So find the average value of this function, y(e) to the xy plus 6 over the rectangular region, where x is between 1 and 3 and y is between 0 and pi. And you know if your region is rectangular, which I think for double integrals, he never gave you something that wasn't rectangular, you can kind of do the double integral in either order you want, right? You can switch it without having to think about like changing the region. So we should kind of take a little bit of care here to do a couple things. First of all, I remind you that the average value is equal to 1 over the area of your region, or you're dividing by your area of your region, times the volume of your double integral. So it's your double integral over your region of your function, and then d whatever, dx dy, dy dx. And then I'd probably take a minute since it's a rectangular region, or even if it wasn't, but especially since it is, I'm gonna take a minute to think about which way it's going to be easier to anti-differentiate this function first. So I'll point out that if I anti-differentiate this with respect to y first, for y(e) to the xy, I'm going to have to do integration by parts. So I should probably just assume it's going to be x first, just probably going to be easier, and it is. So also, I'll point out that the area of my region, here, the area is going to equal 3 minus 1 times pi minus 0, which is just 2 pi. There's a rectangle, it's a rectangle, right? Base times height. So then the average value is going to equal 1 over 2 pi. I decided I'm going to integrate with respect to x first. So x is on the inside, y is on the outside. So it's the integral from 0 to pi for the y's, then 1 to 3 for the x's. My function is y(e) to the xy plus 6. I said I was doing x, so x is inside, so dx dy. And now we're going to integrate. Do I have enough room? Maybe. So I get 1 over 2 pi. The integral from 0 to pi stays out here. We're going to integrate y(e) to the xy plus 6. When we integrate y, well, specifically when we integrate e to the xy, because y is acting like a constant as far as x is concerned, the antiderivative of e to the x times a constant is e to the x times that constant divided by that constant. So what's going to happen when we integrate y(e) to the xy is we're just going to get e to the xy. So we're going to e to the xy plus 6x, evaluated from 1 to 3 d1. And again, you can double check that for yourself, right? If you took the derivative of this, oh yeah, the derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff, which is just y in this case. We carry on, we get 1 over 2 pi, integral from 0 to pi, we plug in 3 for y, for x, we get e to the 3y plus 6 times 3 minus e to the 1y plus 6 times 1. I decided to take an extra step when I did this and simplify it further by subtracting 18 minus 6. It's probably not super necessary, but I would write this as 1 over 2 pi integral from 0 to pi, e to the 3y minus e to the y, and then 18 minus 6 is 12. We continue, we integrate again, we get 1 over 2 pi. The integral of e to the 3y is e to the 3y over 3. The integral of e to the y is e to the y. The integral of 12 is 12y, evaluated from 0 to pi. We plug in, and we get, I feel like I wrote this wrong in my solutions here. Just double, no, as I'm looking here, I just want to make sure I didn't do any silly. Where are my solutions? Sorry, one moment here. Oh, there we go. Nope, I didn't. I just imagined I did. Okay, so we get e to the 3 pi divided by 3 minus e to the pi plus 12 pi. And then minus e to the 0 is going to be 1. So 1/3 minus e to the 0, which is 1, plus 0. Yeah, I didn't simplify that as much in my notes, but same idea. And I wouldn't do any more, right? There's no real need to simplify this further unless you are specifically asked to. I don't imagine you will be asked to, but you could be. If I was going to simplify this further, there's really not, actually, there's not, I mean, the only thing you could really do to simplify this further, honestly, is make this a minus 2/3, so plus 2/3. Other than that, I guess you get a common denominator, but it really doesn't simplify any further. All right. For those of you in the room and for those of you on Zoom, if you have questions, you should ask them. Otherwise, I'm just going to keep on going. So let's look at this next one here. Which of the following systems of differential equations as matrix, oh, sorry, write each of the following systems of differential equations as matrix equations and state whether or not they are homogeneous. So typically when you're writing this as a matrix equation, you're thinking of, let me zoom in here. Oh, there's something in the chat. 1 second here. So let's see, we have, can you explain again why the y went where? Sure. So let me just grab a piece of paper over here. So what happened was, just like when you do the integral of, say, like e to the 5y, and you get e to the 5y divided by 5, in a similar way, the integral of e to the xy with respect to y was e to the xy divided by the sorry, I apologize. Let me back that up. It was x, not y. So if we're integrating e to the xy with respect to x, we're going to get e to the xy divided by the coefficient of x, which is y. But we also had a multiple of y out in front. Sorry, you can't quite see that. Apologies. So since there was a multiple of y, what really happened was when we integrated y e to the xy, the constant y hung out, and then the antiderivative of e to the xy was e to the xy divided by y, and then those y's divided to 1. So we ended up getting just e to the xy. That makes sense? I hope so. Great, good. Glad to hear it. So moving along. This next one, when we're writing a system of equations as a matrix equation, we're thinking of writing it as the vector dx1 dt dx2 dt equal to some matrix multiplied by x1, x2, and then possibly plus some other vector over here. Also, I remember last week someone asked, like, or maybe earlier this week, someone asked about, like, if nonlinear differential equations can be homogeneous or not. And really, we don't use that terminology for nonlinear. It's really only for linear ones, whether or not there's something added on here that's non-zero. So in this case, if we write this over here, we're going to get, let's see, I have 2t cubed multiplied by x1. I have 5 multiplied by x2. And then in the second row, I have 4 times x1 and negative 3 times x2. There's nothing over here, or if you want, you can say you're adding on the vector 0, 0. Since that's 0, 0, that means it's going to be homogeneous. I wouldn't really write that normally, but I just wanted to point out that if you're adding on the 0 vector, it's a homogeneous system of differential equations. So this system is homogeneous. It doesn't matter that there's a weird T there. That doesn't have anything to do with being homogeneous or not. It does mean it's not autonomous, but that doesn't really, we don't really care at this point. We'll do the next one. Same idea. We're going to write dx1 dt, dx2 dt as a vector. And it's going to equal a 2 by 2 matrix multiplied by x1, x2, potentially plus some other stuff. Let's see. So for the first row, I have 6 times x1 and 4 times x2. So I have a 6 there and a 4 there. And that 5 doesn't get dealt with either of those pieces. So we have to have a plus 5 over here. And then for the second row, we have 2 times x1 and negative 7 times x2. And then that minus 8, again, doesn't get accounted for in that 2 by 2 matrix. So we need a minus 8 over here. And because that is not the 0 vector, our system is not homogeneous or non-homogeneous. We have a non-homogeneous system here. Not a lot else to say about that. I can't imagine him right. So again, most of these questions were taken or kind of reconstituted from the solutions I saw that he had given last time. I could certainly see him asking something like this. The next question was also something else, but I don't feel like we've talked about it a whole lot. So let's kind of go over that. So the next one looks like this. We've got this first part that says to construct the corresponding matrix for the following matrix diagram. And I know we talked about, I don't know. I think we talked about matrix diagrams in 17B, but I don't think we've talked about them in a while, right? I don't think he's taught. Has he talked about this in class? Okay, he has. Okay, cool. Yeah. So either way, it's not too hard to suss out what's going on here. All you're thinking about is what's going into A and what's coming out of A. So if we're thinking of like how A is changing, I usually write it as dxa dt. That's usually how he writes it as well. So let's see. What's going into A? Well, A itself 4 times. So you have 4 times xa and 3 times whatever B is. So plus 3 times xb. But then we're also losing 2 of xa. Minus 2xa. Simplifying that down or combining like terms, we would write this as 4 minus 2. So 2xa plus 3xb. Similarly, dxb dt. So the things going into b, well, we have 4 of b itself, so 4 times xb. We also have 2 of a going into b, so 2 times xa. But then we're losing 3 of b to a, so we're subtracting off 3 times xb. Combining like terms again and writing them in the same order where a is first and b is second, just like we usually write what x1 first and x2 second. We're going to write this as 2xa plus xb, or plus 1xb if you prefer. Keep things in order here. And then the matrix is just going to be the coefficient matrix 2, 3, 2, 1. That's it. Next question. Classify the stability of the equilibrium 0, 0. Now, it's really important to point out here that this question is referring to the matrix we just constructed, right? That first question was 3A. This next question is 3B. Whoever's writing this is thinking they're part of the same question, and there's nothing else to refer to here. So clearly we mean the matrix 2, 3, 2, 1. Let's go ahead and find the eigenvalues. So to find the eigenvalues, we're going to find the determinant of A minus lambda I. We're going to say 2 minus lambda times 1 minus lambda minus 3 times 2. Set that equal to 0. Simplify it a bit. Let's say I get lambda squared minus lambda minus 2 lambda is minus 3 lambda, plus 2 minus 6 is minus 4 equal to 0. Factoring, we get lambda minus 4 times lambda plus 1 equal to 0. So we get lambda equal to positive 4 and lambda equal to negative 1. And we know when our eigenvalues are opposite signs, we have a saddle. So 0, 0 is a saddle. If we were trying to do less work and we felt comfortable with it, we also could have just found that the determinant of A itself is negative. It's 2 times 1 minus 3 times 2, which is negative 4. And that would have also told us that we have a saddle. So I would say when the determinant's negative, it's kind of the best case as far as classifying because you don't have to do any other work. If the determinant's positive, it's probably just easier to find the eigenvalues itself. So if you can look at the determinant real quickly and be like, okay, 2 minus 6 is negative, great, we know it's a saddle. If it had been the other way, like in this next one here, if we look at this, and I will point out, I did change this positive 2 here to a negative 2. I wrote a Canvas announcement as well that should be a negative 2. Otherwise, it was also going to be a saddle, and that just seemed like it wasn't very helpful as far as having you learn something. So if we looked at this one and saw that positive 3 minus negative 10, which is 13, is positive, then I don't think I want to do it using the trace in the term. It's just more work than I really want to do. I want to just find the eigenvalues. So again, find the eigenvalues. So that's going to be the determinant of negative 3 minus lambda, negative 2, 5, negative 1 minus lambda, which is going to be negative 3 minus lambda, negative 1 minus lambda, minus negative 2 times 5 equal to 0. Let's see, simplifying, we get lambda squared. We have plus 3 lambda plus lambda is plus 4 lambda. That seems wrong for some reason. No, it's not wrong. I'm just making up stuff in my head. And then positive 3 plus 10 is plus 13. I will also just mention as a real quick point here, if you wanted to, you could also find this equation by saying it's lambda squared minus the trace times lambda plus the determinant. If you wanted to skip writing out determinant of A minus lambda I, you could do that if that seems convenient to you. You don't need to do that if it doesn't seem convenient to you. All right, so I will notice that we can't multiply the 13 and add it to 4 in any reasonable way. So we're going to use the quadratic formula here. So our eigenvalues are going to be negative 4 plus or minus the square root of 4 squared minus 4 times 1 times 13 all over 2 times. Couple things to think about. We know we don't have a saddle because our determinant was positive or would have been positive. So our eigenvalues are either both negative because that's a negative 4 minus something is certainly negative plus something. Well, if it was positive, then we'd have a saddle. We know we don't have a saddle. Or they are they're imaginary with a negative real part. Either way, we have stability. Although we should be more specific here, since we have a nice 2x2 regular kind of regular linear thing, we should actually say if it's a stable spiral or a stable node. So let's do a little bit more work. We have negative 4 plus or minus, let's see, 16 minus 52 is negative. It's the square root of negative 36 all over 2. At this point, you probably don't actually have to do any more work unless they say find the eigenvalues. At this juncture, we can say, cool, we know that 0, 0 is a stable spiral because the real part's negative and we know the eigenvalues are complex. It's probably not a bad idea, though, to actually simplify this and get, especially since negative 36 is easy, right? It's negative 4 plus or minus 6i all over 2, which is negative 2 plus or minus 3i. So it's probably a good idea to find the eigenvalues if they look easy to find, or even if they don't. But technically, right, if it just said classify, once you can see that the eigenvalues are, like you might write words like complex with a negative real part if you didn't want to actually find them. It's probably easier just to find them than to write those words. So yeah. Is a stable spiral and node the same or are they different? They're different. So a stable spiral is one, let me make sure. So like graphically, when you find a stable spiral, the direction field like looks like your traces or your paths look like this when you have a stable spiral. Whereas for a stable, and you're going inwards, right? Every initial condition leads to something like that. Whereas with a stable node, you don't circle around, you just kind of point inward. So like if I started somewhere like here for a stable node, I kind of like go in like that, or maybe, like that, depending on what it looks like. But it's definitely not a spiral. You were kind of just going inward towards the origin. Both go in towards the origin. Spirals just have a little bit more circulation. And the way we know the difference, right, is that spirals are going to happen when we have complex or imaginary eigenvalues, whereas nodes are going to happen when we have real eigenvalues and they're both the same sign. And so both positive means unstable node, both negative means stable node. And one of each sign means saddle, which is not a node. If you have the time, I might encourage you to plot some different, like, so if you have a minute, like take this differential equation, the one that we just did, sorry, one sec. Like take this matrix, -3, -2, -5, -1, and plug it into one of those direction field plotters, like -3x minus 2y, and then dy dt is 5x minus 1y, and you'll see that it looks like a spiral. Whereas if you plot something else that, the eigenvalues are both negative or both positive, you can see it's going to be a node. All right. So both negative is nope, both negative is stable, both positive is unstable. So negative, whether they're both negative and real, or they're complex with a negative real part, negativity. So actually, let me remind you that negativity right here, this eigenvalue corresponds to something like e to the -2 plus 3i times t, which then corresponds to e to the -2t times e to the 3t times I. And since it's a negative number there, that thing is going to get smaller and smaller and smaller as time goes on and on and on. So as time goes on, we're getting closer and closer and closer to the equilibrium of zero. Same thing is true if your eigenvalue is just a negative number, right? If your eigenvalue is like -5, you're going to get e to the -5t, and that's going to go to zero as time goes on and on and on. Whereas if your eigenvalues were positive or had a real positive part, that thing's going to blow up to infinity instead of getting closer to zero. So I'm saying very, very emphatically here, negative things correspond to stability. Positive things correspond to instability. And if you have one of each, it's a saddle, which is also unstable. Okay, let's look at the next page. I want to keep these notes in order here. All right, so solve the following system. Solutions will be complex. They probably won't tell you that on the exam, but I felt like it was just in case you've done it on your own and you want to be like, well, maybe they're not really supposed to be complex. No, they're definitely complex. So let's go ahead and find the eigenvalues. We're going to have determinant of 3 minus lambda, -2, 4, -1 minus lambda. That's going to equal 3 minus lambda times -1 minus lambda minus -2 times 4. And then we simplify this, it's lambda squared. -3 lambda plus lambda is +2 lambda. And then -3 plus 8 is +5. Double check, I'm not making a mistake. Nope, we're good to go. So then using the quadratic formula, our eigenvalues are going to equal -2 plus or minus the square root of 2 squared minus 4 times 1 times 5 all over 2. That's going to equal -2 plus or minus 4 minus 20 is -16, and the square root of -16 is 4i all over 2. So our eigenvalues are equal to -1 plus or minus 2i. Great. Now we need to find an eigenvector, and just one, right? Because it's a complex situation where we just find the one eigenvector. So we're going to use lambda equal to -1 plus 2i, and then we're going to throw that into our usual equation. So we're going to say that our matrix 3, -2, 4, -1 multiplied by the eigenvector that we're trying to find is equal to -1 plus 2i times the eigenvector that we're trying to find. That is the way he tends to prefer to do it, even though I think kind of doing it the other way is usually easier, but this way is also pretty straightforward. I will say when you do this, you really should only write one of the equations, right? You don't need to write both 3 times v1 minus 2 times v2 equals -1 plus 2i times v1 and 4 times v1 minus 1 times v2 equals this times v2. You only need to write one of those equations. So let's write the first one. So we're going to say, great, 3 times v1 minus 2 times v2 equals -1 plus 2i times v1. Bring all the v1s to the same side. And be careful. So if I subtract v1 over to this side, I should say, if I subtract 3v1 over to this side, the -1 minus 3 is going to give you a -4 real part. So we're going to have -2v2 equal to -4 plus 2i times v1. And I do think it makes sense to divide both sides by -2 here, since we have a coefficient of 2 for everything. You can pick 2 or -2. I would generally pick the thing that left the real part positive if I had the option to. So dividing by -2 gives me v2 equal to 2 minus I times v1. And then our vector is going to equal, I'm going to pick v1 equal to 1, and v2 is going to be 2 minus I. I feel like I'm making a mistake here. Yeah, I know. I remember getting this. Let me double check what I'm doing wrong. I'm definitely making an error. Is it right? Exactly. So this is why it's important to check your work carefully here. So I should have had 3v1 minus 2v2 equal to -1 plus 2i times v1. Oh, thank you so much. Yeah. How did I get negative? What did I do there? Oh, right. So right here, is where I missed something. I had somehow I said +3 minus 1 when it should have been -3 plus 1. That should have been a -2. Oh, it's terrible. So then that should be a +1 plus or minus 2i. A +1 plus 2i. +1 here. +1 here. And then finally, we're going to get to -v2 equal to 1 minus 3, which is -2 plus 2i times v. And then dividing both sides by -2, we're going to get v2 equal to 1 minus I times v1. So my eigenvector should be 1, 1 minus I, not 2 minus I. Good catch, everybody. And then he prefers to write it as the real part, or the real vector part, plus I times the imaginary part, which would be 0, -1. Now we're going to write our solution, our general solution. So general solution, that's where you're writing your x of t. We don't write the c, or he doesn't write the c. It's just your e to the lambda 1, which is 1 plus 2i times t times your vector. And then I would try to do this writing as little as possible, right? Showing enough work, but like Normally, if I was showing this as an instructor, I'd probably write like e to the t times e to the 2t times I. I'm going to skip that and write that as e to the t times, I know that the e to the 2t times I is going to be my cosine of 2t plus I sine of 2t. If I was worried I might make an error or that someone didn't know that knew that I was knew if someone grading it didn't know that I knew what I was doing, I might write above this. Oh yeah, that's my e to the 2t times I. So that they know that I know what I'm doing. And then still times this, your 1 plus I times 0 -1. And then I feel like he writes this kind of weirdly. Because he yeah, how does he write this? I'm always kind of like, yeah, but he does something else first. I just want to make sure. Let me just double check one thing because I want to make sure I'm kind of doing it the same way he is. Is that what I'm looking for? No, it's not. Sorry, one moment, please. Just want to check one thing while I make this look as beautiful as possible. I do feel like he does it kind of strangely. Or not so much that he does it strange, just like the steps are kind of just not quite in the same order I would necessarily do them in. And of course, this thing isn't loading now. So, okay, well, fine. Let me just look at this here. There we go. So let's see. That's not what all, there we go. So from this step, he typically then, no, okay, he just leaves the E to the, okay, so, all right, cool. I was just imagining things. So he then usually does this. He writes it as e to the t, and then he just FOILs it out. So you're going to have, and I would FOIL it out in a way so that I got my real parts first. So I'm going to have cosine of 2t times the real vector there. I times I is -1, so I have negative sine of 2t times that vector there. And then I have, and I would probably factor out the I, but whatever. You're going to have I sine of t, sorry, sine of 2t times 1, and then you're going to have I cosine of 2t times 0 -1. And then we usually say, great, the real part, or he says, I don't know if I love doing it this way, honestly. The real part is g of t equal to this first part here, e to the t times cosine of 2t times 1 minus sine of 2t times 0 -1. And the imaginary part is h of t equal to e to the t times all the stuff here without the I, right? So it's sine of 2t times 1 plus cosine of 2t times 0 -1. And then our solution, our general solution is x of t equal to c1 g of t plus c2 g h of t. And I guess those are vectors. And it feels like he hasn't really been asking you to find particular solutions to these imaginary ones. Like it feels like for the complex ones, you're not usually given an initial condition to solve for. That doesn't mean he couldn't ask you to do it. I certainly have here. It's not terrible, so let's do it. This is where it's super important to remember cosine of 0 is 1, sine of 0 is 0. So if I just plug in t equal to 0, I'm going to get x of 0, which is equal to 5, 7. That was given to us in the beginning of the problem. And it's going to equal C1 times G of 0. Okay, let's look at G here. G of 0 is going to be 1 times 1 minus 0 times it doesn't matter. And then C2 times H of 0 is going to be 1 times 0 times 1 plus 0, sorry, cosine of 0, which is 1 times 0 -1. It doesn't always work out so nicely, but in this case it does. Fun fact, and this will probably happen. It might happen. If one of these numbers is 0, it's really easy to figure out what C1 and C2 are. You both should be able, you all too. Oh, sorry, 1 second. If I had a vector 1i with separation of the real, yes. If you had a vector 1i, the separation would be 1, 0 plus I times 0, 1. Yeah, that's totally right. I'm here. Both of you and you all on Zoom should be able to tell me right now what C1 is equal to without doing any work. Right, C1 is 5. And if you know C1 is 5, then 5 plus C2 times -1 should equal 7, which means C2 has to equal -2. So C1 equals 5, C2 equals -2. If it were me, I would personally want to write my solution the long way, which is kind of annoying. I would want to write it as 5e to the t times all this garbage minus 2e to the t times all this garbage. But if you've already said what C, G, and H are, it probably is smarter to write x of t as 5g of t minus 2h of t. And then we'll look at the non-homogeneous one. And here's what I'll say about the next one we're about to do. On the solutions I posted, I did it kind of the long way where we make a substitution. We got like y equals something, y1 equals something, y2 equals something. I'm going to not do it that way right now. I'm going to do it the faster way so you can kind of see that. But I'll then talk about the other thing. All right. Let's move on to the last question. So, solve the following non-homogeneous system, again, with initial conditions of something. The initial condition you should just ignore until you get closer to the end of the problem. All right, so to start off a non-homogeneous, you typically want to start by finding the equilibrium. So the equilibrium, just set each of those two differential equations equal to 0. So we have -3x1 plus 4x2 minus 2 equal to 0. And I'm going to not write the 0x1. I kind of wrote the 0x1 there just to make it super clear that a matrix is going to have a 0 there. If you miss that 0 there, it's easy to put the 2, I should say the -2 in the wrong spot in your matrix. So just be careful if you're missing one of your variables. Make sure you get your other coefficient in the right spot. Here we have -2x2 plus 10 equal to 0. So I think we can easily see here that x2 should equal 5. And then if we plug that back into the other equation, we have -3x1 plus 20 minus 2 equal to 0, or 18 is equal to 3x1, so x1 is equal to 6. So that's our equilibrium, 6, 5. So I would point out that our x hat is equal to 6, 5. Do make sure you get the order right. I know I wrote x2 first and x1 second, but x1 has to go on top. Now I'm going to skip the work of doing the substitution, of letting y equal x1 minus 6 and y2 equal x2 minus 5. Because I don't think you need to show that work. I could be wrong, but maybe he wants you to show that work. I don't think you need to though. Sure. Okay. So now to solve the system, we're just going to use the matrix -3, 4, 0, -2. We're just kind of ignoring the -2 and 10. And we are in luck. We already know the eigenvalues. They're -3 and -2. So let me be consistent here. Lambda1, I think I called -3, and lambda2 is -2. So I don't want to do oppositely. Yeah. Lambda1 equals -3, and 2 equals -2. Let's find the eigenvectors. So our eigenvectors are going to be -3, 4, 0, -2 times your first eigenvector is going to equal -3 times that same first eigenvector. And looking at the first equation, we get -3 times V1 plus 4 times V2 equal to -3 times V1. The V1s cancel, leaving us with 4 times V2 equal to 0, which means V2 is 0, and our vector is the vector 1, 0. So our V1 vector is 1, 0. That's almost always going to happen when you have one of these 2x2 matrices with a 0 in the lower left corner or the upper right corner, is one of your eigenvectors is going to be either 1, 0 or 0, 1. Always happens that way. For the other eigenvalue, we're going to have -3, 4, 0, -2 times V1, V2 equal to -2 times V1, V2. Looking at the first equation, we have -3 V1 plus 4 times V2 equal to -2 times V1. And then if we add 3 V1 to both sides, we get 4 V2 equal to 1 V1. So our eigenvector for the second eigenvalue is going to be V2 equal to 1, V1 equal to 4. I will mention that in this, for this second part here, for the second eigenvector, if you use the second equation, it wouldn't have helped you. The second equation would have been 0 times V1 minus 2 times V2 equals -2 times V2, which just tells you that -2 V2 equals -2 V2, which doesn't help. So sometimes with these situations where you have a 0 here or a 0 here, one of the eigenvectors, you're going to have this thing where one of the components is 0 and the other component is 1. And the other eigenvector, one of the equations doesn't help you find it at all. And the other equation tells you what it is. So just be aware of that. If you see a 0 there or a 0 there, be mentally prepared for like, oh yeah, one of the eigenvectors is kind of this weird thing, and the other one of the equations doesn't help. So if one of the equations doesn't help you, just move on to the other equation. All right, let's write the general solution. So we're going to have our general solution, and I'm going to write x. So your general solution is going to be your usual deal. Let me think about this for a second here. I just have to make sure I do this the right way. I have to think for a second. No, that's right, yeah. It's your solution C1 e to the lambda 1 times t times v1 plus C2 e to the lambda 2 times t times v2. And then you add on your equilibrium. That's your general solution. You could check it if you really want. You shouldn't check it, right? Like in general, like if you're taking a test, you shouldn't check it. But if you actually checked it, it would be true that the derivative of the first equation is equal to -3 times x1 plus 4 times x2 minus 2. And the derivative of the second equation would equal 0 times x1 minus 2 times x2 plus 10. But this is kind of the shortcut way of doing it. And then we have to plug in our initial condition to find our constant C1 and C2. So plugging in t equal to 0, here's what we get. We get x is going to be 11, 8, because that was the given initial condition. And it's going to equal C1 times 1, 0, plus C2 times 4, 1, plus 6, 5. Again, a relatively easy situation to figure out. In fact, if you want to, you can just subtract 6, 5 and say, okay, great. That means 5, 3 is equal to C1 times 1, 0 plus C2 times 4, 1. That means that C2 is going to have to be 3. And then C1, well, it's going to be 5 minus 3 times 4. 5 minus 12 is -7. C1 is going to have to be -7. You could write out the equations. Yes, yeah, good question. So are we adding, so when you find the general solution here in a non-homogeneous situation, you find your general solution in the usual way, and then you slap on the equilibrium that we found. In fact, I would say, so the question was, are we adding the equilibrium only if it's non-homogeneous? And I would actually say the answer to that question is no. We're doing it either way. It's just that if it's homogeneous, what's the equilibrium? It's 0, 0. So honestly, you could think of always adding on the equilibrium to your solution. It's just that most of the time it's 0, 0, so you're not going to write anything. Kind of a good idea. I like good question. Excellent question. I like that. It really helps us, I think. Oh yeah, you just always add on the equilibrium. And then finally, our solution would be that x of t is equal to let me see one thing here. Somehow I got interesting. What dumb things did I do in my solutions here? Okay. How did I do that wrong? No, I'm just yes. Somehow in my solutions I wrote okay, I'll have to fix that. I made a small mistake at the very end of my solutions. Totally fine. So my here we're gonna get C1, which is -7 e to the -3t times 1, 0, plus C2, which is 3 e to the -2t times 4, 1, plus our equilibrium 6, 5. Somehow in my solutions, at the very, very end, I accidentally interchanged where C1 and C2 were, but I'll fix that. So one thing I'll say is that the longer way of doing this, which I don't think he really wants you to do, but I don't really know, to be honest, is where you do this thing where you, after you find your equilibrium, let me zoom in a bit here. So after you find your equilibrium, 6, 5, you then make up new variables where y1 is x1 minus the equilibrium value and y2 is x2 minus that equilibrium value. And then it's just, I feel like it's way too much work to do it this way. So I don't think you should do it this way. But if you knew how to do it this way, wanted to, you certainly could do it this way. It just feels like it's a lot more writing. So that's all I got. I gotta have to fix this thing. Yeah. Yeah. I think that's it. Good luck on Monday. And then after your test on Monday, we'll talk about chapter 12 stuff. Or I mean, I guess we could talk about how the exam went, but it's not really super fruitful to do. So sure you could ask questions about the exam if you want to, but we'll try to do some chapter 12 stuff. All right, have a good weekend, study enough, not too much, get enough sleep, eat some breakfast, all the usual tips. And also the best tip I can give you is make sure you read the questions on the exam carefully. There's probably no other better test taking tip, to be perfectly honest. Read the questions slowly, thoughtfully, give yourself an extra 30 seconds there to save yourself an extra few minutes on the problem, not doing the wrong thing. All right, that's all I got. And I know who you are, so I'll just attend. Don't worry about I got the. I was like, oh, I just won't even pass out the attendance sheet. I know Alexa and Nathan. You're welcome.